Hello, Dr. Lai. I'm Noreen Homaira from KIB1016 with matrix number 24002284/2. I will be talking about MOSFET in insulin pump. So this is the insulin pump as you can see on the top right diagram. That is the device. An insulin pump is a medical device designed to help diabetic patients manage their condition more effectively. Instead of relying on multiple daily injections, the pump provides a convenient alternative by delivering insulin automatically through a small catheter placed under the skin or labeled here as the cannula. The system works in close coordination with glucose sensor, which continuously monitors blood sugar levels. The sensor sends data to an algorithm, in other words, the microprocessor, aka the brain of the system. The algorithm acts like the decision maker, analyzing the readings and determining how much insulin is required at any given moment. The pump itself is usually worn on the waistband and connected to the body with tubing. Inside, it contains a storage of insulin and a motor that pushes the medication through an infusion set. The infusion set includes a tiny cannula that sits just beneath the skin in the fat layer, allowing insulin to be absorbed steadily and naturally. This design provides several important benefits. It reduces the need for manual injections, which can be painful and inconvenient. It also ensures more consistent insulin delivery, helping patients maintain stable blood glucose levels throughout the day. By combining sensor feedback, smart algorithms, and precise electronic control, the insulin pump offers both safety and comfort, making diabetes management more efficient and less disruptive to daily life. Now let's see how the insulin pump operates. So insulin pump works by combining user input and sensor feedback to deliver precise dose of insulin. First, the user programs the pump with their basal rate and bolus request. At the same time, continuous glucose monitoring provides real-time data about the blood sugar levels. All of this information is sent to the microcontroller, which, as I said just now, it acts as the brain of the system. The microcontroller processes the data and decides when insulin needs to be delivered. It then supplies a voltage to the MOSFET's gate terminal, and this voltage opens the switch, allowing current to flow to the motor. As a result, insulin is pushed from the storage into the body. In short, the microcontroller uses voltage control through the gate terminal to ensure insulin is delivered precisely. Now, let's see how the MOSFET play a part in this system. So, MOSFET is a metal oxide semiconductor field effect transistor. It has three terminals, which is the gate, the drain, and the source. The gate is insulated by a thin oxide layer, and when the microcontroller applies a small positive voltage to it, an electric field is created. This field will attract mobile electrons under the gate, forming a conductive channel between the drain and the source. As a result, the resistance will drop nearly to zero, and current can flow through to the motor. When the motor receives this current, it pushes out a microscopic droplet of insulin. And on the other way around, if there is no insulin needed, no voltage will be sent to the gate terminal and there will be no electric field. When there is no electric field, the resistance will remain high, no current will flow, and the switch will remain off. So, in simple terms, the MOSFET acts like a control doorway. A microcontroller decides when to open it with voltage, and that allows precise insulin delivery exactly when needed. Next, let's look at how the pump avoids delivering way too much insulin at once. The microcontroller uses a technique called pulse width modulation or PWM. Instead of keeping the motor fully on, it rapidly pulses the gate voltage. For example, if the motor is on for only 10% of the time and off for 90%, it only receives 10% of the effective power. This way, the pump can push out insulin in very small, controlled microdoses. By adjusting the ratio of on time to off time, the system ensures precise delivery that matches the patient's needed. Now, here we want to see why we use MOSFET in this medical device and why not other transistor. Uh, we are comparing MOSFET with BJT here. Now, first, let's look at the control mechanism. A MOSFET is a voltage control while a BJT is a current control. This means that to switch a MOSFET on, the microcontroller only needs to apply a small voltage at the gate. In contrast, a BJT requires a continuous input current at its base. For a battery powered device like an insulin pump, minimizing current draw is critical. MOSFETs consume far less power, which directly translates into longer battery life for patients. Next, input current. MOSFETs require a very low input current, almost negligible, because the gate is insulated by an oxide layer. BJTs, on the other hand, need a higher base current to operate. This difference is important because insulin pumps must run continuously, often 24 hours a day. Using MOSFETs ensures the electronics remain efficient and don't drain the battery unnecessarily. Third, switching speed. MOSFETs switch faster than BJTs. This speed is essential for techniques like pulse width modulation, where the motor is pulsed rapidly to deliver insulin in microdoses. A slower device like BJT would struggle to keep up with the precise timing, potentially affecting the accuracy of insulin delivery. MOSFETs, with their fast response, guarantee that each microdose is delivered exactly when needed. Finally, power efficiency. MOSFETs are highly efficient compared to BJTs, which are only moderately efficient. In medical devices, efficiency isn't just about saving energy, it is about reliability and safety. A more efficient transistor means less heat generation, less wear on components, and more stable operation over long periods. For a patient relying on their pump every single day, this stability is non negotiable. So, when you put all these features together, voltage control, low input current, um, faster switching, high efficiency, it is clear why MOSFETs are the better choice for the insulin pump. They allow the device to be compact and wearable and reliable while ensuring precise insulin delivery with minimal power consumption. In short, MOSFETs makes the pump safer, more efficient, and more patient-friendly compared to BJTs. So, to conclude, the design of an insulin pump highlights how electronic components like MOSFETs and pulse width modulation contribute to efficient and reliable medical technology. The system's use of MOSFET, which is voltage controlled, provides low power consumption, which allows for longer battery life, making it practical for daily use. And its fast response ensures precise control of insulin pulses, preventing over delivery and maintaining safety. And the miniaturization provides a small and compact provides a small, compact, and wearable device for patients to use, improving comfort and mobility for patients. And finally, its reliability ensures stable operation even under continuous use. Altogether, these features show how small electronic design directly enhance both the performance and usability of life-supporting medical devices. That's all from me. Thank you.